All right, so let's work this problem. Again, we want now we want the slope and displacement at C. That's the free end. So we have the cantilever beam. Got this uniformly distributed load over the first, well, basically half. And over the second half, nothing's going on. They've got this concentrated load at the end. So let's think about this one for a second. If we did direct integration, how would we work this? Yeah, I have two sets of equations, and again, I'd have to get those four integration constants. That may not be a bad approach. If you like solving simultaneous equations, that's for you. What about conjugate beam? Well, you can imagine what the moment diagram for this is going to look like. A constant load becomes linear shear, and linear shear becomes quadratic moment. So you have a quadratic loading curve for the M over EI. Probably not something you want to do. So maybe conjugate beam would not be good for this. However, our new friend, virtual work, doesn't care. We're going to write a set of moment equations from A to B, and a second set from B to C. We're going to find the virtual moment equations, multiply them together, integrate, we're done. So again, the virtual work can be a little tedious, but it's kind of the multi-purpose tool. It can handle everything. So before we get started, let's see what we're going to need. So I'm thinking about writing moment equations, so I'm probably going to cut the structure somewhere between A and B. Do I want to work the left side or the right side for A to B? Is there an advantage or a disadvantage? Well, if I go left, that thing get unfocused? There it comes back. The moment will be pretty straightforward, but I'll have to have both reactions. Well, not both, moment reaction. If I work the right-hand side, I won't need them. But this little sliver here might be a little interesting. So you'll have to decide which way you like. I think from B to C, it's straightforward. You work the left side or the right side. I think the right side there is a slam dunk. So I'm going to save a little time in my mind, and I'm going to go right on both of them. So I don't have to find any reactions, just to kind of show you a different approach. So the first thing I'm going to do is find the real moments. So the first one's going to be between 0 and 7. And I'm going to cut it here and work the right-hand side. So that'll leave me a little sliver of the distributed load, and then on the right far end, the 75 kilonewton force. And then, of course, I'm going to come up to this edge, and this will be X. The remaining piece here will be 14 minus X. And then what's this little piece right here? We know this is 7. So it looks like it's going to be 14 minus X minus 7, which is 7 minus X. You guys follow that? This whole piece here is 14 minus X. And you subtract away part you know is 7, then this piece is left with 7 minus X. Okay? I'll just have to write it here to the side. So I'll want the concentrated equivalent load of that bit here. That'll be the force. And of course I want the distance from the centroid, from the edge. And what we're looking for here is the real moment. So I'll come underneath here. We'll sum moments at the cut. Make sure it's in equilibrium. Okay, what do we got? We got the moment. And with my sign convention, that's negative. The force, which represents this little piece of the distributed load, is also creating negative moment. What is the force? Well, it's 25 kilonewton meters times that distance, which is X minus, so it'll be 25 times 7 minus x. That's the force. And then what's the distance d? Well, it's this distance divided by 2, which again is 7 minus x. Except it'll be divided by 2. And then out here on the end, there's the 75. And what's the total distance to there? 14 minus x. So when I solve for the moment, I'll just move that to the other side. So this all becomes negative. So I'll take that 25 divided by 2, which will give me 12.5. And then I'll have 7 minus x squared. Minus this one, I'll just leave it alone. 75 times 14 minus x. And I'm not going to waste any time expanding that, trying to make it nicer, because it's so fun. It's the moment expression. Now, one disadvantage of this particular method is now I'm not quite sure what this is going to tell me, because I'm cutting it here, and I don't know the moment anywhere. The only place I would know the moment would be at the reaction if I solved for it. That'd be at x equals 0. You can put in x equals 0, and you'll see you'll get a value. Oh, I left off sign here. Sorry, this is negative. Negative 12.5. But I don't know what it is. So maybe I should have solved for the reaction just to be able to check. Right now I'm just going to have to leave it alone. I don't know anything else. So let's come over now and go from 7 to 14. That's this one. We decided to cut here, and again we wanted to look at the right-hand side. And now this one just has the 75 kilonewton reaction. So at some distance x to the cut, I'm left with this little segment. Again, that's going to be 14 minus x. And then internally, there's my maximum moment. Well, you can see right away that's a little easier to deal with. So if I sum moments at the cut here, what do I get? Well, that's a negative moment. 75 creates negative moment at a distance of 14 minus x. So it looks like the moment here is negative 75, 14 minus x. Well, now you can check something here. If you look at the right end, we know the moment at c is 0. And that's at x equal 14. You put in x equal 14, you get 0. Okay, we know that one's good. But we can check these two. We know that the moment at the point they share at b should be the same. That's 7. If you put in x equals 7 here, this term dies off, right? And you're looking at negative 75 x plus 14. And this one's the same. So it does that you put 7 in there, it'll be the same. So it looks like this one's it's okay too. See that? So I'm feeling pretty good. I think those real moments are valid. So let's do the next part. Let's do the slope and displacement. So what do we want to do? Let's do displacement first. So what's the virtual beam look like for displacement? Well, the geometry is the same. So there's my beam, fixed on the left. Unlike conjugate beam, I don't have to do anything there. And I want the displacement at C, which is the free end. So I'll go out here to the free end, and I'll assume that it acts down. And, of course, our virtual force is always 1. How many equations do I need for this beam? One equation. If you cut it, you want to work the left side or the right side? I think the right side is best. So in this case, I'm going to have one element that's going to be good for all 14 feet, and it'll look like this. There's my right-hand segment. There's my virtual load of 1. Remember, we're cutting it at any arbitrary x we want between 0 and 14. So the remaining piece here should be the length 14 minus x. And of course, if you sum moments at the cut, make sure it's in equilibrium. I did leave out one thing. I forgot to put in my internal moment. And that's lowercase because it's a virtual moment. So you'll have negative moment, and then negative 1 times the distance, 14 minus x. So again, now my virtual moment is just equal to, this looks like x minus 14. I just ran the minus sign through. And can I check that? Or what's the moment at the free end? 0. That's at x equal 14. You put x equal 14 in. What do you think the moment is at 0? It would just be force times distance, which is 14. Of course, you put in 0 there, you get 14. That's right. That works. So how do I find the displacement at C? I'm going to integrate from 0 to 14, the length of the beam, the real moment times the virtual moment over EI. Can I integrate the whole length? No, because the real moment changes. It's one value, it's one function from 0 to 7, and a second function from 7 to 14. So I just have to split it into two pieces. This time I will factor out the EI because it is constant. So I'll get first the integral from 0 to 7. This is my real moment, this big long thing. So give me a second to write that down. 12.5 times, 7 minus x squared minus 75, 14 minus x. So that's the real moment. And the virtual moment from 0 to 7, what's this, right? Dx. And then plus the integral from 7 to 14. What's the real moment? That negative 75, 14 minus x. And then again the virtual moment, x minus 14. So again, for my money, you're done. I'll consider this to be the virtual work expression. And again, you can see there's the real moment from 0 to 7. There's the real moment from 7 to 14. And then there's my virtual moment, which is the same throughout the whole structure. And again, I'll go back to the office later today, and I'll finish this off and give you the numerical value, because I did give you a value for I and E. But that's good enough for today. Hopefully that demonstrates the concept, and you won't get too tied up in all these details, because this would take some time to do, right? I don't know about you guys, but I can't integrate this right off the top of my head. So I would be inclined to want to factor this out and turn this into just a quadratic equation, which then would be very easy to integrate. But still, the evaluation would be tedious, especially this one. Whenever you have to do the upper limit of the whole thing minus the lower limit of the whole thing, it's just prone for error, calculation error. And at this point, I don't need for you to demonstrate that to me. Mastering Engineering will still want you to demonstrate that, but you'll have more time. Now this is just half the problem, because we also want the slope. So what do we do now? Well, we still have the real moments. That hasn't changed, so we can use those again. So what I'll just write so that you'll see it is the slope now is going to be equal to what? Well, it's going to be the integral from 0 to 14. It's still going to be the real moment, but now it's going to be the virtual moment due to a rotation divided by EI dx. So we're going to have a different virtual structure. Okay? So let's start again. So the virtual beam here for slope will look like this. So we'll still have our cantilever beam. I want the slope at C, which is here. So I'm going to apply a unit moment at C. Okay? And I'm going to just put a positive right-hand rule moment on there. Again, it's going to have a weird unit. It will have a length unit, but it will not have a force unit. Now, the reason I like to do this one positive is because how's it going to make this, bless you, how's it going to make that beam displace if you curl it like that? Is this point going to move up or down? Up. So the displacement will probably look like that. What kind of slope is that? That's a positive slope. So I'm assuming, unlike I did for the force, I'm assuming that this moment will get a positive force, slope, sorry. If I get a negative value, that means I have negative slope. Now looking back at the real beam, what do you expect to actually happen at C? Is this point going to move up or down? It's probably going to move down, and you should expect negative slope. So I'm expecting this result to give me a negative value. So what are the moments in this beam? So again, I'm going to cut the structure. You want to work the left side or the right side?
Right side.
Right side. If you work the left side, you're going to have to come over here and find all these reactions. So let's go left. We'll also only need one expression. So this will be valid over the whole length, 0 to 14. And my structure will look like this. I've got the applied moment on the end, and I'm going to cut it at an arbitrary distance x, and the segment to the right would be length minus x, which in this case is 14 minus x. And then I'm going to have internally the virtual moment due to the rotation, and I'll assume positive sign convention for that. Like we've done a few times before, we're going to sum moments at the cut we just made. And what do we have? We've got the internal moment, but with this sign convention, that's negative. And what else do we have? We've got the applied moment, which is positive. So it looks like the internal moment is simply just 1. So now we can bring this down, and the slope at C is the integral from 0 to 14 of the real moment, the virtual moment due to the unit couple, divided by EI, and I integrate it. So just like before, our real moment is only valid, one's valid from 0 to 7, a second one from 7 to 14. So we're going to break this up into two pieces. So the first, I almost did it again. I'm going to pull out my EI value. That's a 1. So I have my first integral from 0 to 7 of the real moment, which is this thing. I know you guys can't see it right now, but I'll go ahead and write it in. So it's minus 12.5. 7 minus x, that's squared, minus 75, 14 minus x. So that's the real moment. And then what's the virtual moment here? 1. And then from 7 to 14, the real moment is minus 75, 14 minus x. And the virtual moment is 1 dx, and then we close up the bracket. So again, there's my real moment from 0 to 7. There's my real moment from 7 to 14, two different equations. And then there's my virtual moment due to the couple. It's the same throughout. So again, if you could do that integration, you would get rotation at C. So again, I'll do that one for you too and provide a calculation just to show you that. But if I gave you this on the exam, again, all you'd have to do is just stop at this expression. I think on the exam I'll just call it the virtual work expression or the virtual work equation. I may say the virtual work integral just to make it clear. Any questions about that? It's really quiet today.
Monday.
Is it Monday?
It's Tuesday.
It feels like Monday.
Indeed.
All right.